Hello students, welcome to the IMS GATE Academy. So this session will be going to our lecture number 3. Basically the foundation course of the electrical machine, that is a magnetic material. Alright, so it will going to be the lecture number 3rd. So how many of you are enjoyed the lecture 1 and lecture 2? Please let me know. And also please confirm by hitting the like button how many of you are present. Alright, so that I come to know that you are enjoying the session, liking the session, and each and everything you are liking about the electrical machine. Alright, so we have almost completed chapter 1, sorry, not a chapter 1, lecture 1 and lecture 2, which is the basics of the electrical machine. Alright, so please let me know by hitting the like button how many of you are here. And guys, please do share the session link with your friend so that also they will going to get the advantage of each and every topic or content that we are dealing over here. Do it fast, I am waiting. Alright, and also inform them to join as quickly as possible. Definitely we will going to have a good and a healthy session. And if you are new to our channel, then please do subscribe our channel and also press the bell icon so that in future whenever we are coming up with the live session or with any new initiative, you will come to know instantly. Alright, so shall we start? We have completed 2 lecture 1 and lecture 2. In the lecture 1, we discussed about the important points related to the GATE exam, means the topics of the and the syllabus as well of the electrical machine that we have discussed in the lecture 1. And in the lecture 2, we had discussed about the electrical material, and in that we have discussed what material that we should go for if we are looking for the electric current. Alright, so those who have not watched till yet, after the session, after this session will going to be over, please do watch that one. Alright, so in this lecture we will going to discuss about the magnetic material, and as you know that by the term magnetic itself, the material which allows the magnetic lines to flow inside the material. Alright, so what do you mean by magnetic material? The material which is used or the material which can allow the magnetic field to flow through itself is known as magnetic material, which I have written over here. Then see, any material that exhibits a magnetic property is known as magnetic material, and this property arises from the alignment of the magnetic moment. What is magnetic moment? I will let you know after a couple of minutes. First, let us understand the thing that with respect to their definition. All right. Within the material, there are 3 main types of magnetic material. So how many types of magnetic material that we are currently having? 1, 2 and 3. First one is the diamagnetic, second one the paramagnetic, third one is the ferromagnetic. So what is the diamagnetic? The diamagnetic material is a material which have their property to align the dipole in opposite to the applied magnetic field. So those material which is under the presence of magnetic field or under the presence of magnetic field, under the presence of magnetic force, when the dipole of such material align opposite to the magnetic force, then those material is known as diamagnetic material, which is written over here. What is the example? Examples are copper, gold and silver. So those who have already studied about the electrical machine, or you can say the basics, then definitely they are knowing that to make the material that is used to make the thing in the transformer, which is useful for the flow of magnetic flux, you can say, is the iron. Alright, so why we have not used the copper? This is the reason. Alright, in the transformer, the frame, the yoke and the limb that has been made by the iron frame. Alright, not by the copper, and this is the reason. Next one is the paramagnetic material. What do you mean by paramagnetic material here? The paramagnetic material is a material which aligns its dipole uh, in parallel under the applied magnetic field or under the applied magnetic force in parallel, but the magnetic strength is not as that much stronger when it is compared with the ferromagnetic material. All right. So, what are the example of paramagnetic material? Aluminium, platinum and titanium. Next one is the ferromagnetic material. So, the ferromagnetic material is one of the important material that is used to make the frame of the transformer of any kind of machine you can take where the magnetic flux is to be flow is the ferromagnetic material. And what is the advantage of the ferromagnetic material? That it have strong magnetic properties and exhibit permanent magnetization even in the absence of external magnetic field. So, even if you remove the magnetic field, the ferromagnetic material will have some kind of magnetic field in itself, which is known as residual magnetic field or residual flux density or residual flux, which is usually known as capital B suffix R, BR. Alright, and what is the example of the ferromagnetic material? Iron, nickel, not Nikhil, nickel and cobalt. Alright, so these are the types of magnetic material we are having, and one more type that we are having and which I have not listed here. The reason is those material are not used mostly in the electrical machine. So, this is the reason why I have not listed over here. Now, what is that material? That material is the ferrimagnetic material. See, this is ferro, replace O with I, it will become ferri. So, ferrimagnetic material. So, all in all, we have total 4 type of magnetic material in our electrical machine. Done. So, anyway, I will discuss the ferrimagnetic material. Do not think in such a way that whether the sir will going to discuss or not. Definitely I will going to discuss, as I have promised you that I will going to cover each and every bit which is required for the electrical machine considering to the basics point. So, moving ahead with the first material that we are having, just a second, that is a diamagnetic material. So, what is diamagnetic material? The diamagnetic material is the material which are not having a dipole in itself. Sir, if they are not having the dipole in itself, then how it will going to be magnetized? We have studied in class 11th and 12th that whenever, means basically in the physics, that whenever any material is attracted towards the magnet, then definitely it is due to the dipoles. If there is no dipoles, then how it is or how that material is known as a magnetic material? The reason is that, just a second, the reason is that, okay, before that let us complete the theory part here. A diamagnetic material has a substance that exhibit a weak repulsion, see, repulsion or repulsion towards an applied magnetic field. So, the repulsion here is very weak. Alright. And what is repulsion? Suppose if the magnetic field that you have applied is in a forward direction from left to right, then the diamagnetic material dipoles will align in opposite direction like this. Clear? Now, when placed in a magnetic field, the diamagnetic material generates a magnetic field in the opposite direction, causing them to repel from the magnetic field. This property is due to the presence of paired electron in their atomic or molecular orbital, which results in a net magnetic moment of 0. Alright, and the diamagnetic material are not permanently magnetized and lose their magnetic properties when the external magnetic field is removed. So, what are the examples that we have already discussed? The organic compound, water, gold, copper, silver and bismuth, mercury. Now, let us understand why they are weakly towards the magnetic force. Now, see, before that, what was the example that I was having for the diamagnetic material? The example was, just a second, was the copper. Okay, now under the absence of magnetic field, under the absence of magnetic force or magnetic field, which is denoted by H, let us say this as external. Okay, under the absence of external magnetic force, means here H external is 0. Then see here, this is a material that you are having. Just a second. And there will be no dipoles present when the external magnetic field is 0. Let us say external magnetic field is EXT. Then, now what will going to happen if you apply the magnetic force? So let us apply the magnetic force here. So let us take the direction of magnetic force will be from left to right in this manner. This is H external direction. This means that this is not equal to 0. Then in such cases, whatever the dipoles that we are having in the diamagnetic material, it will align in opposite direction. See, north, south, north, south, north, south, and so on and so forth. Why you have made north in the left side and south in the right side? The reason is, in the magnetic materials, suppose this is your magnetic magnet, north and south, and outside we have an air. Then magnetic field will move out from the north, enter into air, and it will again enter into the south, and in the material itself it is moving from south to north. So if the magnetic force, the extramagnetic force is from left to right, then the magnetic dipoles has to be aligned from right to left, which is represented here. Done? So this is known as, basically, see, the magnetic force generated, sorry, the magnetic field generated inside this is represented by H internal. This is H I and T. H external that we have applied, and H internal that has been created by the material itself, but the direction here will be in opposite. Now let me introduce one important point, which is magnetization. And this is represented by M. Okay, so what do you mean by magnetization? The ability of dipole to align. Please listen me very carefully. The ability of dipoles to align under the presence of external magnetic force. Under the external magnetic force. Done? This means that uh, the ability to align this dipole under the presence of external magnetic force is represented by capital M. Now, let me introduce one formula here, which is M vector equal to chi. This is chi M H vector. All right. So here H is what? External magnetic field that we have discussed, and what is M? Sorry, not M. Where XM is what? This is magnetic susceptibility. I hope you have heard this word, that is magnetic susceptibility. Susceptibility. Just a second. So what this magnetic susceptibility implies? It implies that for same magnetic field, how your material or dipole is magnetized, means how strongly your dipole is magnetized, that is given by the xm, and this xm is what? Scalar in nature. Done. Now see here, as I told you, the direction of M and H, see here the external magnetic field is towards right hand side, but the magnetization that is happening in the material is towards left hand side. So both are opposite in nature. As H, basically this H is what? H external, this one. H and M both are opposite hence they are represented by negative sign. Done. Now since this is the vector, so these two will going to be in opposite direction when we have a negative sign, so we are left with xm only. So whenever this xm is less than 0, then the value will become negative, so it makes that M and H both are negative. So this implies that xm is less than 0. This is very, very important point. All right. This is, just a second, let me write some word upward. Done. Now let us introduce one more point, that is relative stability. Relative permeability. Actually, sorry, permeability, which is represented by mu. Mu r. Okay. So what is relative permeability? Anyone? What is relative permeability? The relative permeability gives the information about the resistance towards the flow of magnetic flux. Whenever the flow or you can say the opposition for the magnetic flux is lower, then mu r will be high. Or whenever the opposition to the magnetic flux flow is higher, then mu r will be low, or if the flow if the opposition is lower, then mu r will be high. So it gives information about the resistance towards the flow of magnetic flux density. Done. All right, so here mu, which is equal to mu naught times mu r. What is mu naught? Where mu naught is relative permeability of air, which is equal to this value is very important, 4 pi into 10 to the power minus 7. What is the unit? Henry per meter. All right, and this is the mu r, which is relative permeability of the material, and mu is the total permeability of the material. Now, as we know that this mu is mu naught times mu r. All right, and one relation between the mu r is 1 plus chi m. This is the one relation that we have known from the electromagnetic field theory. So, we have a relation mu r equal to 1 plus chi m. Now, since the chi m is negative, the chi m is less than 0, this means that this will be negative. So, can I say, if this is this means that this is less than 1, this is less than 1, if xm is negative. So, this implies that your mu will be less than mu naught. Sorry, just a second. See, since this is less than 1, so anything less than 1 will become less than mu naught. So, this is a reason why your relative permeability of the material, of the diamagnetic material, will be less than air. Okay, done. And let me introduce one more thing about the diamagnetic material. Just a second. Okay. Let me rub all this thing. This is not required. Please wait, please wait. Let me rub all this thing. This is not required. Now see, one term let me introduce here again, that is B, which is magnetic flux density. Which is represented by B. And from the electromagnetic field theory, we have a formula of B as B equal to mu H. Isn't it? This we have seen already in the electromagnetic field theory. Now, what this magnetic flux density implies? It implies that how densely your magnetic fields are in air as well as inside the material. Means it refers the closeness of magnetic field with respect to each other. So, it represent the closeness of magnetic field lines lines with each other. With each other. All right. Now, see, for the air, let us take for the air, this relation will give us mu naught H. H is what? External magnetic field, and mu naught is relative permeability of the air. And for the material, let the magnetic flux density, okay, for diamagnetic material, this is equal to mu H. What is mu? Mu is mu naught mu r H. Since this mu naught will be greater than mu r, so can I say this magnetic field dia will be less than magnetic field in air, magnetic flux density in the air. Done. Now, what we understand by this? What we understand by this? Let us take this is your material. Okay, let us take this is your material. Now, this is your diamagnetic material. This is your diamagnetic material. Now, outside this, we have an air. This whole thing are air. So, in the air, the magnetic flux density will be greater. This means that the closeness among the magnetic field line will be higher. So, if you represent like this is magnetic field lines. Okay, just a second. Done. So, outside this, we are having the closeness with respect to magnetic field. So, this is magnetic field in air. But inside the material, this will going to diverge like this. Like this. Like this. Now again, as soon as it means the magnetic field lines move out from the magnetic material, it comes to air, and again it will going to tends towards each other like this. So this is your magnetic field lines, this whole thing, and this one is what? This line is B of dia. So I hope this is clear to you. Alright, so guys, please do share the session link with your friend. Do it fast. So this is all about the diamagnetic material, and we come to know that if you use a diamagnetic material, inside the material, the magnetic flux line will going to be diverged, and which is not good for the power transmission. Alright, which is not good for the power transfer. Done. Let us come to the next material, which is the paramagnetic material. So what is paramagnetic material? The paramagnetic material are those which have a weak attraction of magnetic field. This is due to the presence of unpaired electron in their atomic or molecular orbital. When these material are placed in under the presence of magnetic field, the electrons align themselves with the field, creating a net magnetic movement in the direction of the field, and this causes the material to be weakly attracted to the magnet. Alright, and what are the example? Example are aluminum, platinum and titanium. Now let me take an example of aluminum here. Let us take an example of aluminum, which is represented by Al. Alright, Al. Just a second. Al. Now, what is the atomic number for Al? the atomic number is atomic number is 13. Atomic number is 13. And in the orbital spin, I hope you are aware about the orbital spin. The whole element like hydrogen, helium, lithium, boron, carbon, nitrogen, oxygen, fluorine, neon, and so on and so forth, we can represent that all in periodic table. And the number in the periodic table is basically gives you the atomic number. So we can represent all the atomic number or all the element in the spin, or you can say electron orbital order. How? From the Aufbau rule, means, or you can say from the Aufbau principle, he what to say, he let us know that how we can arrange the electrons, whatever electrons that has been possessed by this aluminum, we can arrange those in the electron spinning. See how we will going to arrange. 1s, this is s block, then 2s, 2p block. Just try to memorize the thing that you have studied in the chemistry in 11th and 12th and 10th, 9th, like that. All right. After that, 3s, 3p and 3d will come. Then 4s, 4p, 4d and 4f will come. Now this s block can accommodate maximum 2 electrons. So 1s2. Similarly, 2s2, 3s2 and 4s2. Now p block can accommodate all in all 6 electrons. Maximum 6 can it can accommodate. All right. Similarly, 6 and 6. Increase in the diagonal, in the diagonal, increase the number with 4 by 4, not 4, by 4. So it becomes 10. It becomes 14. It becomes 10. All right. Increase with 4 number. So what this number represent, that each blocks can accommodate maximum number of electron. So if you try to arrange this atomic number, which is 13, in this block, let us see what will going to be happen. So this is 1s, just a second, 1s, then 2s. Now how you will going to accommodate the electrons? You will going to accommodate in diagonal, but from top to bottom, from the right top to bottom, in this manner. In this manner you will going to accommodate, like, see, first, sorry, first you will accommodate in 1s, then after that 2s, then 2p6 and 3s, just a second, 2p6, 3s2, then 3p6, then 4s2, then after that 3d10 and 4p6 and so on and so forth. Like that you will going to adjust your electron. Now let us fill the electrons. First 1s block will come. Okay. In 1s, how many electrons we are having? 2. Maximum it can accommodate. This is 1s. So 1 means 2 electron, means one will be in upward, then another will be in downward. Like this it will going to accommodate. Then after that 2s will come. Then 2p6 will come. This is 2p, sorry, this will be 2p6, that maximum it can accommodate, and after that 3s2, after that 3s2, and after that uh, 3p6, I guess, no? Let us see. Yeah, after that 3s2, after that 3p6 will come. This is 3p6. Now see, in 1s we have total maximum 2 electrons that it can accommodate. Similarly, 2s2, one will be in upward and another will be in downward. Alright, so this is basically what? The direction of electron. Alright, and 2p6. So it will be, this block will particularly divided into 3 parts so that each block can accommodate a pair of an electron. See how you are going to fill. 1, 2, 3, 4 is done. So you are remaining with 9. So first fill in upward direction, then in downward direction. How many of the electrons are completed? 10. After that, it will accommodate total 2 electrons. So all in all, 12 is completed, and we are left with 1 electron, which is placed here like this. Done. So this is basically what? This one, this will be considered in clockwise direction, means the spinning of this electron will be considered in clockwise direction, and the another one will be considered is in anti-clockwise. I hope you are come to know that why we have represented this in upward and downward, means both are in opposite in nature. So one direction or the one electron will move in clockwise, then opposite, or you can say the other electron will rotate in the opposite direction, which is anti-clockwise. And since these two are in pair, na, so this is known as paired electron. This is known as paired electron. All right, and the next one, see here, do we have any pairing? No, we are not having any pairing. So this is known as unpaired electron. Unpaired electron. And the unpaired electrons will give the occurrence of magnetic dipole. Magnetic dipole. Okay, so the unpaired electron will give you the magnetic dipole. All right, now let us move to the next part here. Okay, so the movement of the dipole, let me change the color. The movement of the dipole will be dipole movement will be from south to north, that we have seen in the diamagnetic material. This we have seen. All right. Now, under the absence of magnetic force, when H is 0, this dipole, since we have an unpaired of electron, na, so definitely we will be having the dipoles. All right, we will be having the dipoles. So let us take the dipoles here like this. This is north and south. Similarly, let us take more dipoles. Let me generalize this one: north, south, and so on and so forth. So these are these all are what? These all are dipoles. So whenever you are not applying any magnetic force, the dipole will be aligning in random direction. All right. Now the simpler way to represent this, the simpler way to represent all these dipole is in this manner. See, the direction for the dipoles will be from south to north. So for this part, you can simply use this one. For this part, you can simply use this one. For this portion, you can simply use this one. You can represent your dipole in this manner or in this manner. Both are equal. Done. But what will going to be happen if you apply the magnetic field? See, under the presence of magnetic field, let us take H not equal to 0. Means this is the external magnetic field under for this material. For this material, this will be the magnetic force. And let us take the direction of the magnetic force is from left to right. Done. So as soon as you will apply the magnetic force, then all the dipoles will align in the same direction. See, for this, it will align in this direction. This will also align in the same direction. This will also align in the same direction. This will also align in the same direction. So whatever number of dipoles we are having in the paramagnetic material, those will align in the direction of the external magnetic field. So this means that M is in same direction as that of H. All right. Now we know the relation between M and H. So M, which is magnetization, is equal to mu naught. Oh, sorry, not mu naught, mu H. Okay. Okay. Sorry. Extremely sorry. This is chi, not mu. This is chi. Chi M and H. Chi M and times H. Now, since these two are in the same direction, for opposite we have used negative sign. Then for same direction we will going to use positive sign. So, since this is positive, since XM is positive, this implies XM is greater than 0. XM is greater than 0. Now, one relation we know, mu R, which is equal to 1 upon chi m. Now, as chi m is positive, so can I say this is greater than 1? This is greater than 1. And what is mu? Mu is mu naught mu r. So, since mu r is greater than 1, can I say this mu of the material, of this material will be greater than mu naught? Any doubt so far? Guys, please do share the session link with your friend. All right, please do share the session link with your friend so that also such that they also get maximum advantage from the session. Now let us move ahead and find the closeness of the magnetic field. Now B air, which is mu naught H, and B of paramagnetic material, which is mu naught mu r H. Now since this mu, basically this is what? This is mu H. This mu is what? Mu naught mu r. So since this is greater than mu naught, so can I say this will be greater than your air magnetic flux density? Okay, sorry. Okay, now using this, let us see the magnetic field direction. Now outside we have an air, and this is what? This is a paramagnetic material. Paramagnetic material. And outside we have an air. So see the direction. Like this. Like this. Okay. So outside the strength of the magnetic flux will be lower, but inside it will be more closeness to each other. It will be more closeness to each other. See, so in this case it will converge. It will converge like this. And after that you will be have, just a second. This is magnetic. Okay, and this is your magnetic flux line. Okay, now see inside the material, the magnetic field lines are closing, or it is very near to each other. So the magnetic flux is strengthened inside the material, whereas at outside the magnetic flux lines are more farther from the each other. But if I talk about the value of xm, the value of xm, so the value of xm is very small. Here the in the paramagnetic material, the value of xm in this material the value of magnetic susceptibility is closer to 1, which is very small, So again, this is not suitable for the electromagnetic material. All right, means the material that we are looking in electrical machine. So this is not suitable. All right, now what is the difference between paramagnetic and the diamagnetic? In the diamagnetic, the field lines were farther away in the material, whereas in the paramagnetic, the field lines are more closer to one another. Let me shift to here so that it will be easily visible to us. Done. So this is all about your paramagnetic material. Now let us look into the material that we are using in the electrical machine, and that material is known as ferromagnetic material. So what is the ferromagnetic material? Just a second. What is ferromagnetic material? The ferromagnetic material are those which have a strong attraction to magnetic fields and can become permanent magnetized. This is due to the presence of unpaired electrons in their atomic or molecular orbitals, and the way the electron aligns themselves in the group called domain. What is domain? I will let you know. Please be there for some time. When these materials are placed in magnetic field, the domains align themselves with the field, creating a net magnetic movement in the direction of the field. This causes the material to be strongly attracted to the magnet and can retain its magnetic property even after the magnetic fields removed. So this is the advantage. This is the advantage of the ferromagnetic material over the other. All right. So even if you remove the magnetic field, the magnetic force, then also we are having some kind of magnetization in the material. Done. Now, what are the example? Iron, cobalt, nickel, and any other alloy. So the ferromagnetic material are widely used in the production of magnet. See, it is widely used kind of magnet, all right, and in electrical generator, motor as well, transformer, and other industrial application where strong magnetic field are required. So basically, the ferromagnetic material is a kind of material that we are looking for to be used in our electrical machine, or in the electronic part also we are using this ferromagnetic material. Now let us understand this by taking one example. So let me take an element, a material, iron, and it is represented by Fe. And what is the atomic number for this? Anyone? What is the atomic number? 26. Now in spin orbital form, it is given by, see, it is given by 1s2, let me write it directly, 1s2, then 2s2, then 2p6, okay, just a second. One S2, 2s2, 2p6, then 3s2, then 3p6, then 3d6, and 4s2. Let us see. 2 to 4, 6, 10, 12, 18, 18, 6, 24 to 26. So these are the orbital spin values in terms of their blocks. All right. Now, what is actually happening here? See. This is 1s, then 2s, then 2p6, then 3s, then 3p, this is 3s, this is 2p, this is 2s, this is 1s, and after that 3d will come, 3d and 4s. So it will accommodate 2 electron, then 2 electron, but here it will be divided into 3 separate blocks. So total 6 it will come. Then after that 3s, so 2 will come. Here it can accommodate maximum 6 electron like this, and in D block it can accommodate maximum of how many electron? Yes, total number will be 10. So see here, this will be 1, we require 6 na, 1, 2, 3, 4, 5 and 6. But in 4s we have 2 electrons. So overall we have a 26 number of electron which is inside the iron. Now, if you look at the 3D block, the number of unpaired electrons is higher when it is compared with the paramagnetic and the diamagnetic. So, since number of unpaired electron is higher than the dia and para, so it will have large dipoles which imply more strengthen towards magnetic field or force. Okay, any doubt in this? Done? Okay. Now see, under the absence of magnetic field, when H is equal to 0, means the external magnetic field. When H is 0, the dipoles will align randomly like this. Anywhere it will going to be aligned. Done. But once you apply the magnetic field, now see what is going to be happen. When H is not equal to 0. This is visible? Okay. So, let the direction here for the magnetic force like this. So, in the same direction it will going to align. Whatever dipoles that we are having, the number of dipoles, the same number of dipoles will be aligned in the same direction of external magnetic field. All right, just a second. Now, since the M and H both are in same direction, wait a second. Okay, since M is parallel with H, so this implies XM greater than 0. Now, as magnetization, see, as magnetization here is high, as M is high, then XM will also be high, because M is what? XM into H. So, as M is directly proportional to XM, so if M is high, this can only be possible if XM is high. So, the XM is high because of high number of unpaired electrons. Done. Now, what is mu r? Mu r is 1 plus chi m, and this is very greater than 1, or you can say nearly equal to XM. So, mu, which is equal to mu naught mu r, this is much greater than mu naught. This is much greater than mu naught. Okay, so magnetic field in air, which is mu naught H, and magnetic field density in a ferromagnetic material, which is mu naught mu r H. So this is much greater than magnetic flux density in air. So just a second. So what it implies? It implies that just a second. It implies that if the magnetic field outside, means the magnetic field lines outside the material, if it is like this, see the separation between the magnetic field lines, then inside the material these magnetic field lines are very closer to each other, like this. And when it goes outside the air, it will again going to diverge. Just a second, let me draw. Okay. Done. Now see the separation between the magnetic field lines in air and in ferromagnetic material. Okay, and this is the magnetic field line. Done. Any doubt in this? Any doubt in this? Okay. Now, as I told you that it is having one advantage, and what is that advantage? Now, see here, if the magnetic force is removed, then also some dipoles align in one direction. Look at here in this example, if you make H equal to 0, if you make in the same material, just a second, in the same material, if you make H equal to 0, then some dipoles will align in the same direction, like this. Earlier when H equal to 0 we are having. Okay, just a second. But let us assume that these two dipoles are aligning in the same direction when we have applied magnetic force. So in this direction. Now, due to this alignment of the magnetic dipoles, due to alignment of this magnetic dipole, here B will not going to become 0. B is not equal to 0. Rather, this B is known as BR. which is known as residual flux density, where Br is residual flux density. Done? It is clear? So whatever conception that we are having, that whenever we have a magnetic field, then only means magnetic force, then only at that particular time we are having the magnetic flux density. But in the ferromagnetic material, we have one advantage, which is that whenever you are removing this external magnetic field, then also we are having the magnetic flux density inside the material. And where we are using this concept, we are using we have been using this concept in storing these songs, like पहले था ना कुमार सानू के नगमे. So this concept we have been using from the past decades, like 20-30 years before. All right. So whenever we are not giving any kind of input to the magnetic cassette, or simply you can say cassette, then also we are having the information which is in the which is in the form of song. All right. So this is basically what a kind of song, means this information we can save in our cassettes. This is the reason why those cassettes are also known as magnetic cassettes. All right. So let me add a page here. Now let us see some more point with respect to the material, which is ferromagnetic material. Okay. Now let us see the curve when you are applying the magnetic field force and magnetic flux density. Now whenever you have made one material, which is a ferromagnetic, and for the very first time you are using that material, then at H equal to 0, the magnetic flux will be 0. But over the time, whenever you are using that material, the magnetic curve will go like this. Now suppose you have used for some week, for some month, and for some year, then when you remove this magnetic force, see what is going to be happen. It will not going to be 0 further. So this curve says that whenever you have used this ferromagnetic material for multiple number of times, so when you make H equal to 0, the magnetic flux density will not going to be 0. And this value is what basically? This is Br. To be precise, this curve is like this, sorry. This curve is like this. All right. And this will be minus Br. Okay. What do you mean by minus Br? See, we have applied H not equal to 0 in from left to right. We could have also applied this force from right to left. So for left to right, the Br I have taken positive. Then if you would have applied H from right to left, then in that case the alignment of the dipole will be in opposite direction, isn't it? So this will be represented in minus BR. Okay, so this curve is basically known as hysteresis curve. Hysteresis curve. Or BH curve. Clear हुआ? Any doubt in this? Now, what amount of force we should apply such that this residual flux should be removed? Suppose see, if I am moving in from left to right, see, suppose I am moving in left to right, then to stop me, the force has to be acting in opposite direction. Here the BR is positive, then to make it 0, we will have to apply the force in opposite direction. So this amount of force is required, but in opposite direction. See here, BR is positive now. So to make it 0, we need to apply the negative force, which is known as minus H suffix C. What is HC? I will let you know. In the same way, if BR is negative, then to make it 0, we need to apply the magnetic force in the opposite direction, which is plus HC, and this is known as HC. HC is known as, anybody? HC is known as, please let me know what is HC. HC is coercive force. So if from now onward, if anyone is saying that what amount of force we should apply to make the residual flux, this BR is residual flux, to make the residual flux 0, then you will say that we will have to apply the HC amount of force. This is BR suffix R. Done? Clear? Any doubt? So this is all about the ferromagnetic material, and I hope you know that what is the advantage. Here the advantage is that it is highly magnetized. It is highly magnetized when you are giving the magnetic force. Basically, this magnetic force is what? This is proportional to I, which is current. So whenever the current is flowing inside the material, the ferromagnetic material means whenever the current is flowing inside the ferromagnetic material, actually the current is not flowing in the ferromagnetic material. In the ferromagnetic material, we are wounding the wire. And in that wire, the current is flowing. All right. And due to that current, the magnetic flux is produced, and it will be of higher strength, or it will be high strength in nature. All right. So those all things we are discussing in our online classes or offline classes. This much kind of detail is not required for the basics. Basics is only about to develop the concept. All right. Those all things we are discussing in the transformer. So if once you will going to enroll in our courses, whether that is online or offline, and if you want to enroll, the description is going on at the bottom of this lecture, or the screen, you can say. So there you will find the details. So you can contact, and you can get counsel yourself. All right. So this is all about the ferromagnetic material. As I told you at the beginning of the class, we have one more kind of material, which is ferrimagnetic material. But this material that we are not using for making any means basically the application of the ferrimagnetic material is not at that much of extent if it is considerable if it is considered in the electrical machine. All right. So for the electrical machine, only the ferromagnetic material is having the vast advantage. All right, now let us discuss about the ferrimagnetic material. What do you mean by ferrimagnetic material? The ferrimagnetic material is a material that exhibit a unique magnetic behavior. They are similar to the ferromagnetic material, but the one key difference is that the magnetic movement of the atoms or ions in the ferrimagnetic material are not aligned in the same direction. What do you mean by the magnetic movement? I told you in the paramagnetic is that one means whenever we have a electron in the S block, P block, then the electron can move in the clockwise direction or it can move in the anti-clockwise direction. So that is basically a magnetic movement. Done. In the ferrimagnetic material, the magnetic movement of some of the ions are aligned in one direction, while the other aligned in the opposite direction. This results in a net magnetic movement, but it is weaker than that of the ferromagnetic material. So this is the reason why we are not using this material for making the frame of the transformer or synchronous induction or DC machine. The ferrimagnetic material can be found in natural minerals such as magnetite, which is having the chemical composition of Fe3O4, and ferrite such as Fe2O3 or CO cobalt, I guess Fe2O4, and so on. They are also used in various applications such as data storage, microwave devices, and magnetic sensors. All right, so let us discuss something about this. Let us assume that you have applied the magnetic field in upward direction like this. Just a second. Magnetic field in upward direction like this. Then the magnetic dipoles of the material will be aligned, some in upward and the paired electrons in downward, like opposite. Let us draw some more electrons. Okay, now if you see the upward direction and the downward direction, the net result will be what? The upward direction will give the more number of strengthen when it is compared with the downward direction. So basically, the net magnetization is in upward direction, like this. This is what? This is M. All right. So this means that M vector is parallel with the H vector. All right. And this implies XM is greater than 0. But due to cancellation of this means due to the cancellation of this downward dipoles, what it will make? It will make, but it is less than ferromagnetic material. magnetic material. So this implies that mu r of ferry is less than mu r of ferro. So magnetic field of ferry, just a second, let me shift here. So this implies that magnetic flux density of the ferry is less than magnetic flux density of ferro. Okay, but what is the advantage if over the means what is the advantage of the ferro magnetic material apart from this? One advantage is that flux, which is this is magnetic flux. Okay, this is magnetic flux, which is equal to B into A, means area of the material. So this implies, see here, this is very important point. So this implies your B, which is equal to phi upon A. So what it gives information, the total number of flux, see, this is the total number of flux, magnetic flux passing through per unit area gives the magnetic flux density. It means that, see, suppose you have this number of magnetic lines. So for per unit area, suppose you are taking this area. So the number of magnetic lines passing through this area is known as magnetic flux density. Done. Now what is the advantage? For the same flux, if you are taking the ferromagnetic material, see here, for the same flux, if flux is same, if phi is same, then the magnetic flux density for ferro will be higher than the magnetic flux density for the ferry, isn't it? So for same flux, phi as B of ferro is higher than B of ferry, this implies area of, isn't it? The area of, if this is higher, so area will going to be lower for same flux. So area of ferro will be less than area. This is area of ferry. So this is a huge advantage of the ferromagnetic material. So whenever the area is going to be reduced for the same flux, this means that the size of the machine will going to be reduced. If the size of the machine will going to be reduced, then the material that we are going to be used for making the material is also going to be reduced, and effectively the cost for making the material will going to be reduced. So this is the great advantage of the ferromagnetic material. All right, so with this we have completed the magnetic material. All right, so I hope you have enjoyed, just a second, I hope you have enjoyed the session over here, which is a magnetic material, and those who have not watch the lecture 1 and lecture 2. Please do watch the lecture 1 and lecture 2 and share the session, all the session with your friend, so that they also may going to get the maximum benefit from the initiative that we have taken. All right. So guys, do like the session, do share the session with your friend, subscribe to our channel, and also press the bell icon so that you will going to be instantly notified whenever we are coming live or whenever we are coming with the new initiative. All right. So in the next lecture, I am going to start the important basics, or you can say the rules of the electrical machine, and also the laws of the electrical machine. All right. So what is the laws in the electrical machine that we are having? Faraday's laws, Biot-Savart's laws, Ampere laws, and also the rule, that is Fleming right hand rule, Fleming left hand rules, and Fleming right hand palm rule. So those all rules and the laws I will going to discuss in the next lecture or session, you can say. So if you are not aware about the session date and timing, you will find the playlist of mine, and in that all the playlist has been created. So you will going to find the date and also the timing. All right. So the timing will most probably be from 1 to 2:30, means it will start from 1 p.m. and it will end till 2:30. So please come on time, so that you should not lose any kind of concept, and whatever doubt you are having, definitely you can post and I will rectify all those doubts during the live session. All right. So bye bye and take a very good care of your health.